Okay, can you hear? Obrigado. Onde está o seu paper?
Já abriu? Não, acho que abriu alguma coisa de research.
Voltamos. Okay, everyone, now David is going to present.
Okay, so I'm gonna talk about this paper that I wrote last year. That is a multi-component security wind dark matter and direct neutrino masses with an extra abelian gauge symmetry. So in this paper, we propose a model that contains two dark matter candidates and generates a direct neutrino monster at one loop level. And it also contains a other sector with two component dark matter and two mediators, the dark Higgs and the dark photon. And we study the whole phenomenology of the model, and we compare with theoretical constraints and cosmological constraints also. So when you the first thing that we want to establish is that as I think that you already know, the standard model has two phenomenological problems: the lack of a viable neutrino mass term and the lack of a viable dark matter candidate. So we want to establish a model that solves the both problems at the same time. For this reason, we use a kind of model that is called a security wind dark matter, where it's a typical model where the processes that lead to the relic abundance of dark matter are in the dark sector rather than in the visible sector. The dark matter particles can annihilate into metastable mediators that finally decay into standard model fields. So we want to study the extensions of the standard model with an extra abelian gauge symmetry. The introduction of an extra abelian symmetry generates chiral anomalies. The chiral anomalies can be, in this case, can be rewritten in terms of the two Diophantine equations shown in the first term. That is the condition for anomaly cancellation in this model, where psi I are a set of charges which represents the charges under the dark symmetry, the extra-abelian gauge symmetry of the chiral fermions. For example, if we consider this set of standard of these 15 fermions, we can prove that this set of charges is anomaly free, satisfy the equation 1, and they can acquire masses through the Higgs mechanism. a Higgs doublet with a hypercharged theory that give Dirac masses for 14 14 of the fermions, of the chiral fermions, that in this case, this symmetry is exactly the standard model case. You want the hypercharge with the, we have 3 pairs of up quarks that are degenerated because of the color symmetry, and 1 electron. Remember that we are considering just a generation of standard model fermions, and we know also that there is a remaining fermion that leaves massless, that is -3, with charge -3, that represents 1 generation of neutrinos. So what is the idea? We want a model that occurs the same that in the standard model. We want that all the masses in the dark sector will be created by the Higgs mechanism in the in the same way that the chiral fermions with different charges pair up to form Dirac fermions. So, and we want also that the fermion, the models generates the Dirac of neutrinos of delta order. In this case, we consider the delta equal 1, that is 1 loop realization, that can be generated through that Dirac neutrino mass operator that is shown in the equation 2, where W are the Wilson coefficients of that model. So, in this order of ideas, we explicitly started the solution given in the equation 5, when the three we have one dark matter component that is the lightest eigenstate of the mixing of the 1 minus 10 pair of charges that represent a sector, a dark matter candidate way to that is degenerated, that has a degeneration of 2, and the other dark matter candidate is -5, is the result of the -5, -4, that acquired masses through dark Higgs of charge 9, and the right-handed neutrinos of charge 9 remain massless. So explicitly, the field content of the model introduces these 3 right-handed neutrinos, the chiral fermions, but we also need to add at least 1 scalar doublet, the eta, and 1 scalar singlet phi, that in order to realize the that operator for Dirac neutrino masses. So, so the Yukawa, when we add these 2 terms, we generate the 2 Yukawa terms. The Yukawa terms that are shown in the equation 6. That this is a Dirac neutrino mass model, so the same dark symmetry ensures the preservation of lepton number. So now we are gonna study briefly the mass spectrum of the of the model, we have the Higgs doublet of the standard model and the extra field that gives that is responsible for the spontaneous symmetry breaking of the new symmetry of the U1 dart symmetry. And here, and then we have two Higgses that are gonna mix, and when we diagonalize this matrix, we gonna obtain two physical math eigenstates. One of them is the Higgs of the standard model, and the second one is a new dark Higgs that it will be unstable because it can decay into right-handed neutrinos. So we also have here the mass matrix for the inner scalars. We consider also that inner scalars are too heavy in order that they don't interfere with the Dark phenomenology, that they are not the Dark candidates and they don't interfere with the Dark phenomenology. So this scheme shows what I'm trying to say. Two Dark candidates in the Dark sector, one C1, and the other one has the two Dirac fermions C1 and C2 that mix, and the lightest state of day is gonna be the harmonic candidate. S and C prime would be the mediators that keep the two dark matter candidates in thermal equilibrium in the dark sector, and they also can act as a portal of communication with the visual sector. If the kinetic mixing and mixing angle between the Higgs and dark Higgs are not negligible. So this is the Feynman diagram that gives a Dirac master for neutrinos at one loop. Okay. The Yukawa couplings are chosen in order to satisfy the constraints due to oscillation experiments. Now, this is the Lagrangian for the new B prime field. I'm showing with also its interactions with the dark septon fermions and the heavy scalars, and I'm showing the important parameter for phenomenology that is gonna be the kinetic mixing between the B prime and the B vector bosons, B from the standard model and B prime from the U1 dark symmetry. So these three bosons, the B prime and the W3 are gonna mix, and they're gonna form 2 or 3 mass eigenstates that are the photon, the C boson, and the new C prime. Now we're gonna talk about a little bit about the dark matter phenomenology. So we have two dark matter candidates. So we will have three kind of processes that will contribute to relative density of dark matter candidates that are annihilation into standard model fermions, conversion between the two dark matter candidates, and semi-annihilation. The semi-annihilation processes are forbidden because of the U1 symmetry. There are symmetry. So are the Feynman diagrams for the charge block diagrams, the diagrams for the processes that lead to dark matter density. For example, annihilation of dark matter particles in the C prime and into Higgses. In the case, of course, that C prime and dark Higgs are lighter than dark matter candidates. So we also have these two diagrams that contribute to conversion processes from the dark matter candidate into another. Now that we have these two dark matter candidates, we have to solve this system of two Boltzmann equation for each dark matter candidate in order to compute the dark matter relic abundance for each of them. It's useful to introduce this ratio for annihilation and conversion, written as in the equation 19 and 20, that gives which are the contribution of annihilation and conversion processes to the total relic density of each dark matter candidate. We also know that the sum of the relic abundance of the two candidates must be the relic abundance of dark matter. So what is important here when we have two component dark matter models is that we have to express the observables in terms of the relative abundance, the abundance of each dark matter candidate, the ratio between the abundance of each dark matter candidate over the total abundance of dark matter. Because it's what actually gonna measure, for example, the experiments of direct detection on indirect detection. So as you know, as I was showing, there are matter analyzing to C prime bosons, which can decay into neutrinos. That's the reason why it's not the dark photon, the dark matter candidate, because it is unstable. So this is the equation 23, shows the decay rate for dark photons into neutrinos. Okay, as for a more simplistic scenario, we want to consider a limit where for example, one of the dark matter candidates would be the most dominant component of the relic density, and the other one is negligible. For example, by considering, for example, that one of the dark matter candidates is very heavy, and we compute the analytical cross section in the scenario, and we show that it gives the right value and it's compatible with the numerical results for a program like Comigas. So in this case, we show the plot of the dark matter abundance for one dark matter candidate as a function of the dark photon mass. Okay, so finally, we use with the called parameter space. We explore the parameter space of the model by considering a variation of the parameters of the model within this range. The C prime boson mass, the the new Dart gauge coupling, the Yukawa coupling of the Dart fermions, the mass splitting between the Dart fermions, the mixing angles in the Dart sector, parameters in scalar potential. We consider also we have to introduce some cubic coupling in the Lagrangian to close the loop of 4 Dirac neutrino masses, and also the Y and L couplings that are the Dirac Yukawa terms for Dirac neutrinos. So as a result, I can show, for example, the graph in the figure 6 that shows the relative abundance of each Dart model candidate. The blue dot corresponds to the first component of Dart model, and the sign dot corresponds to the second component of the model. The sum of them must be near in the range of 0.12. That is the right value for the model. So we also study the distribution for the masses of the two armored candidates, and with the color bar we have the respective weight of conversion processes. The lighter points are the processes where the conversion process between the two armored candidates is dominant, and the darker ones are the points of the parameter space where the armored candidates annihilate directly into standard model fermions. So this is the same plot, but with the vacuum expectation value that breaks the U1 Dart symmetry as a function of Dark candidate. For some benchmark, the dotted lines show the some Yukawa benchmark Yukawa couplings for the Dirac fermions in the Dart sector. Regarding the direct detection, we have elastic scattering. We have scattering with nuclei mediated by kinetic mixing, and Higgs mixing between the two Higgses. We assume a mixing angle between the two Higgses very small, 10 to the -3 or less. So the main contribution to the processes of to the direct detection is given by the kinetic mixing parameter, the most important parameter. So we have this final result where I show the contribution for the first dark matter candidate. The spin independent cross section for the first dark matter candidate multiplied by the ratio of the abundance as a function of the dark matter candidate. And we show here also the limits imposed by Xenon and Thorne, LZ, Darwin, and the neutrino floor. That is the gray band. And we also take into account the constraints due to effective degrees of freedom in the relativistic universe. The magenta region is the one that satisfies that constraints from effective degrees of freedom in the early universe. And the blue zone corresponds to the zone of the parameter space where the kinetic mixing between the standard model photon and the dark photon is negligible. So the colors of the points represent the where the colors are yellow. It means that the two dark matter candidates can be tested in direct detection experiments, while in where the points are blue, it means that only one of the dark matter candidates is testable within dark matters within direct detection experiments. And the same plot here, but for the second dark matter candidate. As you can see, all the region that satisfies the constraint for effective relativistic number of degrees of freedom in the early universe is almost entirely in the neutrino fog, in the neutrino coherent scattering zone. So it means that if we take into account the standard cosmological, the constraint for delta the effective in the standard cosmology, there is a little zone of the parameter space that is not almost always under the neutrino fog. But that constraint could be relaxed if we not consider standard cosmology. So I think that's it. Okay, this plot shows the upper limit of the kinetic mixing as a function of the mass of dark matter candidate, taking into account the constraints for direct detection experiments. So we have a model that can explain both neutrino masses and dark matter in a context of two-component dark matter, where we also analyze the constraints of the model due to cosmological restrictions in standard cosmology, the delta, the relativistic number of degrees of freedom in the early universe, and we also consider constraints from the from direct detection. I think that's it. Thank you.
Questions? I have one. So do you know where the limit from the ineffective comes from?
Is the okay? The you know that we have direct neutrinos, yeah, and there is a restriction that the amount of relativistic species in the neutrino species must be the order of 3. So we have to put these direct neutrinos in just the error bars in the dispersion of the experimental measure from the direct neutrinos. For the neutrino relativity, for the neutrino species, for the number of relativistic species. Or how do I compute that? What's that your question?
No, the point is, so how light are your neutrinos? How light? What are the masses of your neutrinos?
The masses. No, we in this scenario we consider normal hierarchy, and the first neutrino is massless.
Yeah. So where is the constraint from unexpected is coming from? So you don't have new degrees of freedom, right? You don't have. But you do. If ineffective represents relativistic new degrees of freedom, what are the degrees of freedom that are contributing to
I understand now your point. But if they in the early universe they were independent, right-handed and left-handed neutrinos. It's after a spontaneous symmetry breaking that they mix and form direct neutrinos. So it's in the before spontaneous symmetry breaking, there are different.
It's coming from that? Is ineffective though?
Yeah, because it's the constraint for contribution of Dirac neutrinos for the right-handed neutrino.
Okay, because I was thinking that the ineffective constraint would be a result of the Z prime.
No, C prime is heavy.
But the point is because
The C prime is heavy. It must have it must decay before Big Bang nucleosynthesis, so it must be. You can.
Okay.
See.
that should be exactly the reason, because if the case even before the Big Bang nucleosynthesis, it would contribute to the delta effective. So you have to set the bound.
If it was light, if it's too heavy, no, it's not relativistic. So.
Thank you. That's it. So we continue with the streaming, right? And the meetings, okay. And we're going to pass to Heitor. Okay. Yeah.
So, hello everyone. Good afternoon. Today, my presentation is about what can the CMB tells us about dark matter. Actually, a introduction to this topic, more specifically about the chapter 7 and 8 of Barbara's book in cosmology. In so this actually is a study report. I'm reporting what I've studied so far in this topic. So in chapter 7 is about dark matter itself, and what she does here is sum up all the baryonic matter in the universe, and using data from astronomical and astrophysical methods, she comes up to this number that is 0.048 plus this tiny error for the baryonic parameter, the baryonic matter parameter. And what it says is that it is really small because in our benchmark model for cosmology, the lambda CDM, we know that the parameter of matter should be this 0.3, a lot bigger than what we see in baryonic matter in the universe. So that's about 85% of matter that is missing. And exactly this 85% of matter is the dark matter content of the universe. And she proceeds to show the calculations that we do with velocity dispersions of bodies inside galaxies and velocities of galaxies themselves inside the clusters. And she shows that these velocities are way higher than they should be based off the baryonic content of either galaxies and the clusters. So if they're moving too fast, there's a lot of matter that is holding these bodies together so they don't escape the gravitational influence. And this exactly comes from dark matter. And the number now she comes up to, when you sum all the baryonic matter and non-baryonic dark matter inside all the clusters, is about zero point 0.2. So it's a really closer lower limit for the matter parameter in the universe when you count the dark matter in clusters. But what all this has to do with CMB is that CMB is a very strong evidence that these dark matter throughout the clusters in the universe was the CMB is a very strong evidence of dark matter inside the clusters. And now what is the CMB? That is the chapter 8. The CMB is nothing more the photons that we see from the last scattering surface. That is exactly the point of the universe. The point in cosmological scale is like some couple 100,000 years, but it was this moment in the evolution of the universe that it became transparent to light. So here is represented in the right figure. You have the opaque universe here, this outlined circle, gray circle. That is what was the universe before the so-called decoupling event. So before the decoupling, the universe was made of baryons and photons that were very strongly coupled together at this moment until about 400,000 years after the Big Bang. All this plasma of baryons and photons was, what happened was the scattering rate between electrons and photons was too high, and so the photons could not travel freely and the universe was opaque. But there was a moment when the Hubble parameter, that is a function of time that grows with time, that tells us the rate at which the universe expands, there was a moment that this parameter of this Hubble parameter became bigger than the electron photon scattering rate, that is this one in the right, that is inversely proportional to the photon's mean free path. That is the maximum path the photon can travel before scattering with an electron. So that's what tells us when the universe became really transparent. And here is just a table that shows the timeline of these events. So the decoupling I'm talking about happened after the universe was matter dominated. That is this guy right here. And so the universe became matter dominated. And after the recombination, that is when the first atoms formed, so electrons and protons bounded together and create the first atoms. Then you have the photon decoupling, when the photons decoupled from baryons, and the last scattering that was somewhat simultaneous to the decoupling. So that is, the last scattering is when the last photons scatter with baryons, and we see them as the CMB. And as a radiation that we see from Earth, it is pretty isotropic or uniform, in a sense that when we compute its temperature, the temperature of the radiation has a mean temperature of 2.72, about that Kelvin, with an error in a 10 to minus 5 decimal. So it's pretty small. The anisotropies in the CMB are pretty small, really small, compared to the mean temperature itself. But although small, these anisotropies represent the cosmological seeds where the large structures grew from. That is the main idea here. And this analysis that we relate the CMB anisotropies with the large structure dark matter is made with the CMB power spectrum. That is a very famous plot, a remarkable plot of the anisotropies in the CMB. But to understand it, first you have to understand how we measure, how we analyze these anisotropies in the sky. So we take this function that is the fluctuations in temperature normalized by the temperature, and we expand it in a multiple expansion like this. We write it in terms of the spherical harmonics, just like we do in quantum mechanics with the orbitals, just like we do in electrodynamics, right? When we analyze monopoles, dipoles, quadrupoles, etc. So the variable I want to emphasize here is the L, is the angular size. So if L is 1, it is a discrete number, by the way, 0, 1, 2, 3, and so on. When it's 0, you have the monopole. So you are looking at the sky all at once, because the sky for us is just a spherical, just a sphere. Yeah. Anyway, if L is equal 1, you have a dipole, so you have 2 poles, and the M number will give you the spatial orientation of these poles. 2 is a quadrupole. So that is, the important thing to understand is the bigger the L, the smaller is a portion of the sky that you are looking at. So there's the plot where you can see the x-axis is the L variable, that is called the multiple moment. And here it grows in a logarithm scale. And the bigger the L, the smaller are the portions of the sky that you are comparing and computing the anisotropies of the CMB. That's what I've just wrote here. And the thing is, in this graph, it has 2 behaviors. One is before this vertical line, that is the L horizon. That the L horizon is nothing but the L variable that gives me this angular size, the theta horizon, that is precisely equal to that of the distance horizon of the universe at the time of the last scattering. The distance horizon is nothing but the maximum distance a photon can have traveled since the Big Bang to any given point in time. And here the point in time is the last scattering. And this will be important because for angular distance bigger than the distance horizon of the last scattering, the effect that dominates here, that dominates the anisotropies, is the called Sachs-Wolfe effect. It causes this plateau in the graph. It's like it all comes to this mean value of about 30 microkelvin. And for angular sizes smaller than that of the distance horizon at the time of last scattering, you have this behavior of peaks and valleys. And these peaks and valleys are actually acoustic. They resemble the acoustic oscillations that happen in the universe before the decoupling. So I'll bring a little detail on these two. First, the Zarz-Wolff effect that causes this plateau. This is basically because at larger angular scales, the photons are redshifted and blue shifted given the spatial position they were at the time of last scattering. So basically, we consider that dark matter was uniformly distributed in the universe, but with some fluctuations in dark matter density that were responsible for these fluctuations in the gravitational potential. So what's the thing? If the photon was right in the bottom of a potential well caused by accumulation of dark matter, when the decoupling happened, it like climbed up this ladder of potential and it loses energy. So we see it redshifted and we see a cooler photon with less energy. And if the photon was at a maximum of this potential caused by dark matter, it would slide down it and will be blue shifted. It will gain energy. So we observe it as a hotter photon. And what this plateau means is that across different angular sizes, when we go smaller and smaller in the angular sizes in the sky, these potential fluctuations of dark matter remain constant. So it's like a fractal when you zoom in, and every time you zoom in, you see the same thing. So that's what it says, this plateau. For different angular sizes, the potential fluctuations in dark matter remain constant. And this is where it becomes interesting. This should be a GIF. This should be an animation. But basically, dark matter played a role in anchoring the called baryonic acoustic oscillations, because as we know, as it is defined, dark matter doesn't couple with photons. And as the baryon and photon fluid oscillated in the early universe before decoupling, the dark matter, which didn't interact with photons, became like an anchor for these oscillations. And these oscillations themselves happen because, as we learn in cosmology, non-relativistic matter doesn't exert any pressure in the expansion of the universe. On the other side, we have radiation that exerts some pressure at the expansion of the universe. And like this tug of war between radiation and matter, when matter wants to clump up because of gravity and radiation wants to have this pressure, it is the cause of the baryonic acoustic oscillations. And now the peaks and valleys that are more specifically described by these oscillations. So the plateau is where the photons pass through the large potentials of dark matter, and the smaller angular sizes, they are direct consequences of these acoustic, like standing wave oscillations. So the thing is, when the photons are decoupled from a more compressed spot in this wave, like this wave here, they are more dense. They are more densely decoupled. So we observe it as being hotter, as the equation of temperature in function of density of energy goes like this. So if you have more density of photons, you observe it hotter, and the opposite is true. So in a region where you have less baryon photon plasma, they come out cooler. And now the first peak, that is just you have a lot of them, and each of them gives like very important information about the universe, but I'll have time only to cover the first one that happens in about an angular size of 0.8 degrees. And that's about the size of the potential wells themselves. And the potential wells, which caused the larger compression in the baryon photon plasma, are responsible for this highest peak in the plot. And these wells have exactly or somewhat size equal to that of the sound horizon distance at the time of last scattering. And this sound horizon distance at the time of last scattering is just the horizon distance, but instead of the light speed, you use the sound speed at this plasma. So it is the maximum distance a sound wave could have traveled until the time of last scattering. And when we calculate this distance is a proper distance, so we have to integrate it based on the evolution of the scale factor, A. We have this distance of the sound horizon, and we convert it into an angular size using this formula that is just this. The angle is this distance over the physical distance of the object. Here, the object is the anisotropy of the CMB. So we get this angular size, 0.7, that is really close to the angular size of the first peak of the power spectrum. But the thing is, this calculation considers a flat universe. It considers that this angle is like Euclidean. The space is Euclidean, because if the space was positively curved, this angle will be larger. And so the peak, if it will be larger, the peak will be to the left. And if the universe was negatively curved, this angle will be smaller, so the peak will be to the right. So what the position of this peak is telling me is that the universe is flat or nearly flat, is really close to being flat. And on top of that, we can see that the amplitude of this peak is related to the sound, to the sound speed in the plasma. So the higher the baryon to photon ratio in this plasma, the slower the sound speed is. So we can take that information about the amplitude of this peak, and this give off this baryon to photon ratio. And with that, we can calculate the number density of the baryons today in the universe, that is this number, with the radiation number density of the universe today, and we get this number. And with the number density of baryons, we can take the energy density of baryons today to be this, and with this number, we can calculate the baryonic parameter today, that is 0.048 plus or minus this error. That is exactly the same baryonic parameter that was calculated in the beginning. If you remember, it's exactly this, 0.048. So, okay. So this is actually putting a really tight constraint on what should be the baryonic parameter of the universe and the matter parameter of the universe. So the conclusion here is we are most certain about these two parameters, the baryonic parameter and the matter parameter. This one actually was calculated with, as I said, astronomical methods. That is this gray, this faded ellipse here, bigger one. That is the cosmological data from supernova. And the CMB data that I've just described, that is this thinner ellipse, this black ellipse, and the area of them covers this parameter space that I didn't explain exactly this graph, but the y-axis is the dark energy parameter, this one, lambda parameter today, and this is the matter parameter today. So with both supernova data and CMB data, the constraints on these two parameters come really close to, if you see it right here, this dashed line represent flat universes. So if the matter is like 0.8 and the dark energy is like 0.2, we have a flat universe. Every point in this line is a flat universe. And as you can see, these two ellipses converge in a very specific region where the matter parameter is about 0.3 and the dark energy parameter is about 0.7, the lambda CMB parameters. So we are pretty sure that these two numbers are like this. And so this means that necessarily there should be this number of a parameter from dark matter out there And so we have, this is the conclusion. We have very tight constraints that the matter in the universe should be this, and so the missing matter should be this, the dark matter that caused the potential wells in the early universe that we can see with the CMB power spectrum, with either the left side and the right side of the graph, you can see dark matter. And that's it, my presentation. I would just like to emphasize that there's a lot more information in this graph that I wasn't able to understand yet in the time that I had. Like, I was just like to stress that all of this was just overwhelming enough to understand. And it's already some pretty solid evidence, as I said, of the constraints of the dark matter parameter. So that's it. Thank you. Questions?
Really good.
Yeah, actually, really good presentation.
Yeah, that was excellent.
Posso sair agora?
Yeah. You were supposed to present like this. You should have submitted a talk instead of a post.
It's going to speak about research.
Yeah. The spring meet.
Oh,
No, but it's not enough for a spring meet. So someone is asking a question.
Why should not you enter the...
Yeah, it's too late, Frank. Gabi, are you asking something?
So the shadow. The shadow.
Deixa eu terminar.
Okay, eu terminei the YouTube streaming now. Bye. Thank you. all. Pronto, calma.